In our previous video, we looked at how to develop or draw a digraph. Now we're going to look at the focus of this unit, which is creating a schedule. And we're going to first work on creating a schedule from a given digraph. So on the previous video, we had an example. In the example, you had wrecked a car, you went to the insurance company, and they broke it down into these 4 steps of repair. You might remember that the only thing that was important was that we get the exterior body work done before we do the painting, right? Fix the dents before you paint so that task A would lead to task C. Now, once you have this digraph, and we're going to take a look at that digraph in just a second once again, but once you have it created, then you can form a schedule. I'm going to show you how to make a schedule in this video. But one thing to note is that creating a schedule depends on the number of workers. Now, workers we'll often call processors because, well, in any job, it may in fact be what we think of traditionally as a worker, which is, a person, a human, but it could be obviously a robot. It could be a machine. It could be a computer. Anything that is doing the work, we're going to just call it a processor. So how many workers or how many processors are there? Well, if you have one person doing the job, and yes, you're welcome for drawing that beautiful person, then they have to do all 4 tasks by themselves. But if you have 2 people doing the job, then they can tackle those at the same time. Like maybe one of the workers might tackle the exterior body work, right? And they can work on that, while the other worker tackles the engine repair simultaneously. So you're getting the work done faster because they're working at the same time. Now, you could add a 3rd worker, but you might find that if you have a 3rd worker that, maybe they work on the transmission, but then when one of them finishes, they're all like standing around waiting for each other. So we're going to look at those problems. So what I have below are some samples of some schedules from an author. And I want to know which one of these schedules are actually legal. So what I did is I brought the digraph in from the previous video. It's the story of the car being fixed. And so just to remind you what it looks like, A is the repairs to the body being done. A is leading to task C, the painting, right? But you can start at the beginning. You have a choice to start on A, B, or D. Now, which of these schedules are legal? Well, if you look at the schedules, what you have there, you have some new notation. So first off, you have a timeline at the top, right? This kind of shows you time elapsing on the job from 0 up to 13 hours. On the left, you have some labels. They're called P1 and P2. Now, P1 represents processor number 1, all right? And then, of course, P2 is processor number 2. That's what the P1 and P2 represent. So what it means is that you have 2 workers. And so it first would say, well, you assign person 1, right? The first thing is you assign them task A. It's a 4-hour task. Notice that it takes up 4 hours of block. So they're attacking this task right here in the digraph, all right? Whereas processor 2 will be given task B, which is a 5-hour task. Notice it takes up 5 hours in the timeline. They're doing that task. And that's perfectly legal, when I say legal, because at the start, you can go to either one of those tasks. Now, let's go on and look at the schedule. When person 1 finishes after 4 hours, right at the 4-hour mark, they're then given task D. And that's totally fine because you can also work on task D right from the start. So they're given that task. And they're working on that. Notice it's a 3-hour task, so that takes them up to the 7th hour. Notice right here, though, that processor 2 will immediately go to task C upon completing task B. Now, is that legal? Well, if we look at task C, right, this is the one in question. It's a 7-hour task, and the only requirement is that task A must be done first. And in fact, task A was finished at hour 4, so yes, they may begin it at task 5, so that is a legal schedule. So this one up here this one's good, right? This one will work. I want you to notice, though, that in that schedule, it takes 12 hours to finish the job, right? And the other problem is that processor 1 is idle. We have this thing called idle time. I'm highlighting it here yellow. They're idle from hour 7 to hour 12. There's 5 hours of idle time. So that's the downside of the schedule, is that one of my workers is kind of sitting around for 5 hours while the other one is working. All right. So let's take maybe this other schedule on the right. Maybe this one's more ideal. Well, is it possible? Well, notice at the start here, we've assigned player 1 task A and player 2 task D. And that's totally fine because at the start, one person can go to A, and somebody could go to B, although no one's assigned that, and somebody could go to task D. So it's totally fine to assign A and assign D, all right? But at the fourth hour, well, after 3 hours, notice that this person is idle for an hour. So at the fourth hour, both workers are available. So one person is given task B and one person is given task C. Can they do that? Well, yeah, because A and D are both done. The only requirement is that A must be done before you go and do task C. So can I assign it to a different person? Absolutely, as long as the job is done. So this is also legal, right? This is also possible. But notice that now there still is idle time. We have some time down here for this worker and some time over here for this worker, but we're done in 11 hours, right? So this is an 11 hours to finish the job, whereas the previous one was 12 hours. So they're both legal, but notice that one is faster than the other. Okay, let's take a look at some other examples. If you look at these two examples here, you're going to notice some differences, perhaps. All right, they look pretty much the same, but they're slightly different. Okay, which one of those is illegal? Okay, maybe you noticed, maybe you didn't. All right, but the only requirement for this task is that A must be completed before C. And if you look here on the first one, it does look like A precedes C, but if you look here on this one, notice that A does not finish until the fourth hour. Remember, A is the body work, but this schedule is proposing that task C start at the third hour. And so that means we're not done with A before C. So this one is not legal. It's not possible. It's not possible because it breaks the rule of A being done before C. That's the whole point of the digraph, is that A leads to C. So be on the lookout for that. So this one over here seems to be legal. It still has a lot of idle time here, right? And it also finishes at 11 hours. So what you might think of is, well, when I'm creating a schedule, I first can't do an illegal one. It has to follow the rules of the digraph. But I would also be interested in the number of hours it takes to finish, 11 hours versus 12 hours. And I'd also be interested in the amount of idle time, 5 hours of idle time on the first one, a total of 3 on the second and third. All right. And maybe those are the best possible schedules. Let's move on. I've already said this, but to reiterate it, workers completing the task are called processors. All right, processors can be humans, computers, robots, or other machines. And for simplicity, we're going to make very big assumptions that you might have noticed as I've worked already, is that every processor can do every task. All right, we're not going to say that some worker can only paint, maybe they can do everything. And then we're also going to assume that they would all take the same amount of time to complete it. All right, if it's a 4-hour task, everybody does it in 4 hours. We're also going to assume that only one processor can work on a task at a time. All right. So those are big assumptions. And of course, scheduling in the real world is like this, but even more complex because those rules do not apply. The finishing time, we're going to use that term, is how long it will take to complete all the tasks. We're also going to use the phrase optimal schedule, is that notice that there was a bunch of different schedules we could make, but the optimal schedule is the one with the shortest possible finishing time. It's the best possible. Idle time, which I've already referred to as the time in a schedule when there's no tasks available to work on. So somebody just sits around. Okay, so here is a digraph sample. And notice that at the start, you have 3 options. You can go to A, right? You could travel and start working on task A, task B, or task C. And once you're done with A and B, both A and B have to be done before leading to D, and then D leads to F, and then C leads to E, which leads to G. And once you have F and G done, you're done with the project. So that's kind of the order in which it's done. So the question I have, and there's maybe there is a right answer, maybe there's some wrong answers, but how many processors should we have? Should one person work on this job? Should 2? Should 3? And there's an argument to be made. One person maybe looks like they're going to be really busy. We might get it done faster with 2. And you can kind of see that at the end, right, there's kind of 2 main trails that lead to the end. But maybe someone can make an argument for 3 processors, because at the very start, there's 3 different jobs that can be done. But what you'll notice is that later on, there's only 2. So I'm thinking probably 2 processors is the route to go. Although you could make a case for 1 if hiring was too expensive. But I think 2 processors are what I want to use. What are some possible schedules? Well, there are a lot. And then I'm going to put lots, right? And then the hard question is, how might we find the optimal number of processors in the optimal schedule? Well, there you just saw me just kind of like talk about the number of processors, but it turns out sometimes you have to play with it a little bit before you find what's optimal. And what is the optimal schedule? Well, since there's lots of schedules, you have to play with that as well. And that's what we'll be doing as we look at scheduling. So let's take a look. I'm going to drag this graph down. Let's take a look at a possible schedule for this with 2 processors. All right. If 2 processors work, I could assign player 1 to task B at the start. Notice player 1 I'm sorry, I shouldn't call it player one. Processor one is assigned task B at the start. It's a 5-hour task. That means they've traveled this way down the digraph, right? Whereas processor two, right? Processor two is given the large task of doing task C. It's a 9-hour task. So they're going down this route right here, right? Once B finishes at the 5th hour, then they want that instead of giving them idle time, you assign them to another task. What can they do? Well, if you look at the digraph, you can't go to task E until C is finished. You could go to task D if both B and A were finished, but only B is finished. So there's only really one place, only one thing you can assign. You can only assign task A to processor number one. So that's assigned. All right. Then all of those 3 tasks would be completed at some point, A, B, and C, right? All right. Once processor 2 gets done with their task C, what can we assign them to? Well, what's left? D, F, E, and G. Well, which one of those are ready to be done? Well, C leads to E, so we can't get to G or F yet. But D, I can't even work on D yet because D can't be worked on until A is finished. And notice at the 9th hour, right, A is still in the middle of being completed. It's an 8-hour task. So that means the only one possible place that we can go is to assign them to task E, which is a 6-hour task. And then you can see the rest of the schedule play out. As processor 1 finishes at the 13th hour, that means we can get task D done, right? So they're given task D, which is a 12-hour task, right? So they're given that task. But once E is done, they're given task G, which is a 2-hour task. Now, here's the problem. Once processor 2 is done, there's really no other tasks to do besides F. And we can't do F until D is done. So after the 25th hour, there's only 1-hour job left, which is F. You could assign it to either player. Maybe you think, well, we should give it to that person because they weren't doing anything for a lot of hours. But either way, you have a whole bunch of idle time. So it's like, I see I can do it with 2 people, but this idle time is a problem. Is there a way to reorganize or reorder the tasks so that we can get it done faster? And when we get it done faster, there will be less idle time. And that's the big overarching question in this unit. All right. Hope you learned more about how to schedule from a digraph.